My name is Adelbert Chang. I am a data engineer at Target, which is the same Target where you guys hopefully buy stuff. I work on deployment infrastructure there. And today I want to talk to you guys about functors, applicatives, and monads. Now, when I started thinking about this talk a couple weeks ago, I realized I had 40 minutes to cover 3 of probably the most fundamental concepts in functional programming. And I'm aware that braver speakers than I have tried to cover less in more time. Nevertheless, I'm going to attempt to do this anyways, so please bear with me. And I hope that you guys can leave understanding these 3 concepts and understanding why functional programmers care so much about them. So to start things off, we're going to make one big assumption, is that we are interested in doing pure functional programming. Okay? That's sort of the premise of this talk, and then I'll build on top of that. And when we do pure functional programming, we sort of look for 2 properties in our programs. One is that it's sort of like by definition, is that every function in our program is a function in a mathematical sense, which means if I have a function from A to B, and I give it an A, I should get an actual B value back. All right, so this eliminates things like nulls and exceptions. The second thing is for all expressions, say f of x, we want to be able to sort of factor it out in our program. So if I have a larger expression, say g of f of x, I want to be able to pull f of x out into a variable and then substitute e wherever f of x was. And this refactoring should give me the exact same program. So what I've just done is I've said, so like, for example, the first property of saying all our functions must be functions, I've eliminated null and exception throwing. So that's one implication of that. The second implication is we cannot have mutation, print statements, or just side effects in general. So as sort of demonstration, let's say we had a mutable variable x, and then I increment x twice. We can sort of test to see if this meets our criteria by factoring out that increment expression to e and then substituting e to where those 2 things are. And these 2 programs are not identical, right? In one case, you can observe that x is going to be 2. In the other case, you can observe that x is going to be 1. So this violation will happen in general with any sort of side effect. So we can't have that. Now, what I've just done is I've said, all right, you guys can't use nulls, you can't use exceptions, you can't use mutation, you can't have side effects. But what I'm saying is we're eliminating sort of the implementations of these things, but we still want to talk about the concepts they represent, right? So for instance, for null, the concept of a null is useful, right? What null is generally used to communicate is to have a value that may or may not be there, right? So maybe you do something like look up a key in a dictionary and the key isn't there, so you return null instead. But what you're trying to signal is you have no value to return, so you're returning null. So what we can do to sort of regain that power without introducing this weird sentinel value that just magically inhabits every type is we can just make the notion of not having a value a completely separate type. So in Scala, we have this option type where that's sort of separate from A. So if I have an A in a world without null, I can say I definitely have an A, and I can do things with the A, pass it to functions, whatever. And I shouldn't have to worry about it like somehow being missing. And then we have a separate type called option of A, which has either a sum of the actual value we care about, or it has none. And the big difference here is, for one, option of A is a completely separate type from A, which means we can't treat an option of A as just an A and hit some sort of like null pointer exception. The second thing is, in a world without null, when I have an A, I know for sure that I have an A. And then when I have an option of A, I know, OK, this thing may or may not be missing. And so when I go to work with it, I know I have to handle a case where it's not there. We do a very similar thing with exceptions, right? So exceptions themselves we're going to disallow, but sort of the concepts underlying exceptions, the partiality of functions, we still want to have, because not all functions are going to be total, at least in Scala's type system. So we will have some functions that will be partial. Maybe we read from a database and a database is down or something like that. So just like before, instead of giving an A, we're going to return this data type called either. It's going to be either an error or an A. And as its name suggests, it has 2 cases. You either have a left of some sort of error value. Maybe it's a string. Maybe it's like your own data type. And we have a right of the actual value that you care about. And so again, when we have an A, we know we definitely have an A. And when we have something that may or may not fail, we'd return either some error and an A. These are 2 separate types. I can't treat an either as an A. And when I go to work with eithers, then I'd have to handle the error case. Mutation is a little bit trickier, but it's still doable. So we still are going to have computation that needs to have some notion of reading and writing state. places where this may come up are like maybe random number generation, where you need to keep track of some seed value that you generate the random number off of. A more interesting one maybe is like a retry policy, where you have to keep track of how long you waited to retry a request the previous time, and then if that failed again, you know how much to wait the next time. So if you're doing something like exponential backoff, for instance. And so what we can do is, instead of just viewing it as a regular sort of value that can mutate stuff like ambiently, we're going to treat it as it's really a function that takes in the start state and produces a value and the sort of quote mutated state. And we can represent this literally as a function from s to the tuple a comma s, where s is going to be the state we keep track of. So maybe it's long in the case of random number generation, or it's a finite duration for like retry policies. And then a will be like the actual value that we're going to emit, that we're going to produce from that state. So there's a general pattern here, right? For all our functions a to b that sort of do something besides produce a b, so possibly fail, possibly missing, need to mutate stuff, instead of returning just a b, we're going to return sort of an augmented b. So some examples would be like if I have foo, which returns a value that may or may not be missing, I return option of bar. If it can fail, I return either an error or a bar. Or maybe if it needs access to some state, I just return like a state action associated with it. And some terminology that I'm going to use throughout this talk, and that you guys might hear in sort of just talking to other functional programmers. These kinds of functions are often referred to as effectful functions. So option, either, and state are examples of effects. And values without these behaviors are referred to as pure. So the functions here will often be referred to as effectful functions. If we're looking at, say, just a bar as opposed to an option bar, you might hear that being referred to as a pure value. It's just a value in its own right, doesn't sort of have any additional behavior with it. So now we have all these effects. We want to work with them, right? Because we want to do useful things in our programs. So as an example, let's say we're parsing an integer off a string. And if the parse fails, we return none. If it succeeds, then we return sum of the integer. And now we want to say make sure the integer is non-negative. So because we know it's an option int, we can't just say like x max 0, because that wouldn't type check. So we say, all right, if we have a sum, which means we have the value, then I'll do int max 0. But now we have to handle this none case, right? And so with none, unless like we don't have null, we're pretending null and exceptions don't exist. So we can't really like put null here. So what can we do? Well, if we know x is some computation that may or may not, that produces a value that may or may not be there, and y depends on x, which suggests that y itself then may or may not be there. So what we can do is, instead of expecting y to just be an integer, we say y really should be an option integer. And in the case where x does have a value, then y has a value. And in the case where x doesn't have a value, then y doesn't have a value. We do a very similar thing with eithers, right? So either maybe we're reading off config and we're getting the host key and parsing it as well. And if we parse successfully, then we want to add like an API endpoint to it. Otherwise, if we failed, we need to do something with that failure. We can't throw exceptions. So what we can do is do the same thing we did before, is sort of just propagate that error through. Because if we depend on some computation that can fail, then we ourselves can fail. State is a little bit trickier, but it's going to be more or less the same pattern. So let's say we have x, which is going to be some state action that will eventually produce a random integer, right? So remember that state long int really is a function long to the pair int long. And we know if y depends on state action, then y itself should be a stateful thing. And so we can start off by creating a state action. We know that the input parameter is going to be long. We know the return type of this lambda is going to be a pair of a double and a long. So what we can do is run the first state action that we depend on. So we get our random integer and then the new seed that it may emit. And then right before we return it, maybe we want to take the reciprocal of it, for instance. So we just do 1.0 divided by random int, and then we thread the new seed through. So all of these follow more or less the same pattern. We want to apply a pure function to an effectful value. And we can't just do this sort of by the normal mechanism, because an f of a can't be treated as an a. If it could, this whole exercise sort of would be futile. So the whole point is f of a is separate from an a, but we still want to be able to apply functions expecting an a to this value. And so what we've seen is for each f, option, state, either, they have some notion of getting inside the value and observing what that a is. And then in the case where we do have an a, apply the function, and then we're also going to plumb some extra bits through. and these sort of extra bits are the something that the effectful functions do. So for option, it's sort of propagating the effect of not having a value. For either, you propagate the error. And for state, you're propagating the seed, or the state. And so being the good programmers that we are, we see this same pattern occurring over and over again, and we want to be able to talk about them generically. So we unify this pattern into this type class. You can think of it as an interface called Functor. And Functors basically talk about type constructors. So here I call it f. You can substitute f for option, either, state, IO, list, future. And in order to be a functor, you need to support this very generic map operation, where given an effectful value a and a pure function from a to b, I want you to somehow apply that function to the effectful value. So f of a to f of b. So here's an example implementation for option. So for option, we're going to pattern match. If it's a sum, apply the function, rewrap it in a sum. If it's a none, we have nothing to do, so we plumb it through. Similar case for either, where if we have a right, then we can do what we want. If we have a left, we plumb that through. And then similar thing for state. And so with that map operation implemented, we can envision sort of a map syntax that gets put on all these effect types, right? So we can imagine a map method that exists for option, for either, and state. And now what we can do is we can just call map and then just give it the function that we actually care about, and we no longer have to deal with sort of doing the boring plumbing. So in the case of like we parse an integer, I'm going to map over it and then just give it the function I care about. At no point do I explicitly say propagate the none through, because that's sort of boring. Similar with like the config reading, we just say parse my host. If the host exists, I want to tack an endpoint onto it. If it doesn't, then I just get the left of the error message. And for my random integer, take the reciprocal. At no point am I explicitly propagating the new state, because that's all handled under the covers by the map method for me. Drink some water. So functors are all about applying a pure function to a single effectful value. But more likely than not, we're going to want to work with multiple effectful values, right? We presumably will have more than one thing that can fail, or we'll have more than one thing that's going to depend on state. How do I combine those two? So we can generalize what we've been doing to apply a pure n-ary function to n effectful values. And what we're going to do specifically is focus on tupling the values. So I want to implement this operation where given an f of a and an f of b, produce f of the pair ab. And then from there, we can use map to actually go inside the quote, go inside the f, destructure a tuple, and then apply our pure n-ary function. So we're going to focus on just tupling, which is like the simplest thing we can do to combine two effectful values. So we can try to do this generically with just functors. So let's say we have an f of a and f of b where f is functor. And we want to produce f of the pair ab. We're going to need an a to like tuple the values together, so we're going to map over fa. And then we also need a b, so maybe we try to map over fb and pair it up. But this doesn't quite work out, because what we end up with is an f of a and b. And we have, with just functor, we don't know like how to flatten the two f's together. So imagine like this would give us an option of an endpoint. And if we have three effectful values, this would give us option of option, and it gets really nightmarish. So this suggests that we need some additional power beyond functor. So let's look at what this looks like for different effects again. So for option, we're going to have an option of A and an option of B, and we want to get an option of the pair. So in this case, we want to pattern match on the two options, and if they both are sums, then we can pair them up. Otherwise, if either of them are nuns, then we have to thread a none through, which makes sense because if I want to compose two values and either of those values may not be there, then I don't really have a way of composing them, so I have to fail the entire thing. Similar case with either. If I have both rights, then I can do right of the pair of values. Otherwise, if I have an error, then I need to propagate that error through. Because if I want to compose two values that can fail, then if either of them failed, I need to fail the entire thing, because I don't have both values in order to tuple them together. It's going to be a similar thing with state, but again, it's going to be a little bit tricky because we're working with like not a sealed trait. So we'll walk through this one. I have two stateful computations, one that produces an A and another that produces a B. Both depend on some state S. And I want to produce some state action that will produce the pair AB given some state S. So we'll create a state with the current state. We'll do what we did before. We can run the first one, and that gets us an A and the next state. Where it gets interesting now is I can now run the second state action, but I run it against the state returned by SA, which means when I run SB, it can observe any state changes that SA made. So for example, I generate a random integer, and I get a new seed back, and then I generate another random integer. That second random integer gets a new seed, and so you actually get a different random integer. Whereas if I just passed in like current state again, I would just get the same integer over and over. So that's kind of, that would not be that useful. And then now I pair A and B together, and then I thread the final state through. And again, we're going to do the same thing that we did before. These all follow more or less the same pattern. We have a notion of looking inside two effectful values and then pairing them up together while remaining inside the effect. And this is what applicatives are all about. So applicative talks about type constructors that support the zip operation and support the pure operation. So zip takes an f of a and f of b and produces the tuple. So that's the one that we've been looking at so far. And then pure is this one that we haven't really talked about yet. But it basically takes a pure value and lifts it up into the f for some notion of like lifting. And of course, we also want all applicatives to have this map operation, because in order to work with n effectful values, we're going to zip them together so we get a pair. And then we're going to map over it to destructure the pair and actually apply our n-array function. And it also conceptually makes sense, because if we claim to work with n independent effectful values, then I certainly should be able to work with a single effectful value. So here's some implementations for the data types we've seen. For option, it's the pair option that we saw. And then for pure, we're going to just take the A and wrap it up into sum. For either, it's going to be the pair either that we saw. And then for pure, it's going to wrap it in a right. And then for state, it'll be the pair state that we saw. And then the pure is a little bit more interesting. It just takes the state and then produces the value you gave pure without changing the state. Right? So you're sort of, for pure, does the minimal amount of work to take a pure value and lift it into the effect. As a quick note, if you go to, say, CATS or ScalaZ today, or Haskell even, and you look at applicative, what you'll see is this app formulation instead. So what I've presented is zip, map, and pure. What you'll typically see is app. And app sort of has a weird type signature, at least in Scala, where you have a function inside of an f, and then you have an effectful value, and you want to apply the function to that value, all while remaining in f. And this has a nice theoretical story. It sort of has a nicer story in Haskell. It's related. But in Scala, this is sort of makes for an awkward API. And so I like to introduce applicative in terms of zip and map for that reason. I think it makes for a better story. And I think zip is conceptually simpler, because you can sort of see that zip is about composing two values in the easiest way possible, whereas app sort of has a weird signature. That being said, app is, for historical reasons, sort of like the canonical representation of applicative. So if, like, after this talk you go look at what an applicative is, you'll probably see app. As just a quick note, you can implement app in terms of map and zip, like I have here. You can also go the other way. You can implement zip and map in terms of app. And so maybe exercise left to the reader. So here's some stuff that we can do now with, that we couldn't do with Functor, that we can do with applicatives. So let's say I parse two integers now, both of which may or may not fail. I'm going to zip them together and then map over it and then figure out which one of those two integers are larger. And this gives me back an option of an int. I can parse two keys from a config, or I can parse 3 or 4 keys if I wanted to, and then zip them together, map over it, and then get an endpoint. And that gets me either an error or an endpoint. And if any of those parses fail, then I just get the first error that I hit. And then for random numbers, maybe I generate 2 random numbers and then compute the greatest common denominator between those 2 random numbers. And I do this all without sort of not explicitly threading through option or nones or errors or some sort of state seed. I just sort of apply the functions that I care about, and all the plumbing happens for me behind the scenes, because we sort of did all that work up front when we implemented applicative. Now, I've been talking about sort of unifying all these data types under Functor and applicative, but I haven't really motivated why you would want to do that. It's very plausible that maybe you just have zip and map directly on the data type, as opposed to this weird trait that we have. But so I didn't do it for Functor, because Functor is kind of like a boring thing. It turns out you can't really do much with it. But applicative becomes much more interesting. And so we talk about these things in terms of these abstractions for the same reason we talk about any abstraction, right? We want to be able to write functions against these things generically so that anything that implements that gets all these functions for free. So one example is this function called traverse. So I'm going to assume people here know some Scala. How many people have used like future.traverse in the standard library? OK, it's a fair bit. So I've been writing Scala for 6, 7 years now. And by far, the most common question that I've seen at work that people ask me in chat rooms, whatever, is how do I do something like future.traverse, except instead of future, I want it with like option or with either. And in a standard library, you sort of don't get that, right? So the response ends up being, well, you can write your own little traverse option. And then maybe you'd write it like that. And then now you want to do it for either. So then you write another function that says traverse either. And you write enough. So like in my previous job, we had like a file that was traverse option, traverse either, traverse x, y, z. And you look at enough of these and you say, well, there's a sort of common pattern here. We have one thing here that's lifting an empty list into some R effect. And then we have this notion of combining two effectful values. The standard library does not have a notion of, doesn't have an abstraction that talks about these things. So you sort of need to either write these yourselves or reinvent applicative. And so since we have applicative now, we can actually write a generic traverse once and for all. So I went sort of fast for the previous 2 slides, so I'll walk through this one. So traverse list says, given a list of a's and an effectful function, a to f of b, give me an f of a list of b. So I want to apply this function to each element of the list and sort of collect the results along the way for some notion of collect, depending on what f is. So we walk down the list. We start out with an empty b value that we lift into f to start us off. So that's where pure comes in useful. And then for each a that we encounter and the accumulator so far, we apply the effectful function to the a to get our f of b. We zip it with the accumulator, and then we map over it to actually prepend it. So now what we can do is take that single function that we wrote and instantiate it to different effect types. So maybe we instantiate it to option or to either of some error. And so this sort of has, if you look at the type signature, it's sort of like given a list of strings and a function that parses the string into an integer. Give me an option of the list of integers. And this has the effect that if everything parses successfully, then I get a sum of my list of integers. Or if any of them fail, then I get a none at the end. For traverse state, it's for each element of the list, apply this function that needs access to some state to each element and produce some larger state action that eventually produces a list of b. And what's even cooler is as you go down the list, the state action that eventually gets executed for elements further down the list can observe state changes made by elements above. So if I had like a list of, say, a bunch of integers, and I was producing a random integer from each one, as we're producing random integers, it's changing the state behind the scenes, and random number generation down the list can observe C changes made by elements above the list. And so we have radically different behavior for a variety of data types. And these are all backed by the exact same function, right? These are just traverse lists instantiated to different effects. And this is the kind of like code reuse that we wouldn't be able to get without being able to talk about applicatives. So by sort of reifying things that we normally assume to be ambient, we can leverage them to do really cool things. So this is one of like the prime examples of code reuse when we talk about functors, applicatives, and monads. So far I've been talking about applicatives working with specifically independent effectful values. And what this means is we have our values up front, right? F of a and f of b are given to us up front. Our function says, given an f of a and an f of b, give me an f of the pair ab. But what if we wanted to have an fb that is dependent on the value of an f of a? Right? So let's say I have a function called nextStep that takes a foo and produces an f of a bar. And then I have an f of a foo, and I want to produce an f of a bar. So one thing we can try is, well, we need access to a foo in order to produce the bar. So we'll map over foo, and we'll get the x out. And so x is of type foo here, and then maybe we apply nextStep to it. That gets us an f of a f of bar, similar situation to what we landed in before. And we have no notion of sort of smashing together two f's. So like before, this suggests that, and we can try other things as well, but it's not going to work out. This suggests that we need power beyond just applicative. We need something that allows us to compose dependent effectful values, not just independent ones. So let's again look at what this looks like for various data types. For option, given an option of A and a function from A to option of B, get an option of B. So what we can do is pattern match an option. If it's a none, then we thread a none through as before. Otherwise, if it's a sum, then we can produce the next option. And this is sort of where the data dependency comes in, where we can't really produce an option of B without an A being present. So you can begin to see how the existence of options B is dependent on whether or not A is there. Similar case with either. If it's a left, we have nothing to do, so we plumb it through. If it's a right, then we can do the next step of our computation that itself may or may not fail. But the dependency is we need to be able to know what that value is. We won't know until it's a runtime thing. State, similar thing. We're going to walk through this. So we have some state action that's eventually going to produce an A. And depending on what that A is, I'm going to produce some B that itself depends on the state action. So we're going to first run the thing that produces an A. So that gets us A and the next state. We're going to run F against A. So we get our next stateful action depending on what that A is. And then we're going to run that new state action against the state returned by running the first one. All right, so you can hopefully see how this is sort of different than previous ones. We have a data dependency now. And this is what monads are all about. You might hear or see a lot of tutorials that try to make different analogies, but I think the one that sort of clicked most for me is monads are about composing dependent effectful values. So if I have an effectful A and I have a function that produces an effectful B dependent on what that A is, I want to be able to work with those. So that's what flat map is all about. And pure is the same pure that we saw from applicative. And it turns out if you have flat map and pure, we can implement the methods that we saw before, map and zip, which means if you can implement the monad interface for option, either state, you sort of get map, zip, traverse all for free. So this is one of the benefits of abstracting over these things is code reuse. And so now one of the things we can do with with monads that we couldn't do before is do additional parsing. So maybe we parse a header from a file, and depending on what that header is, I'll parse the body in different ways. That's something we couldn't do before. Maybe if I'm reading config, I read this type key, and if that key is service, then depending on what the value of that key is, we'll parse different keys. So if it's a service, then I'll parse the Docker key. If it's otherwise, we assume it's a job, so we parse the job key instead. So what we parse depends on the value of an earlier parse. And then for a random integer example, maybe we generate a random integer, and depending on what that integer is, we generate a random number that's bounded by that integer. Right, so these are things that where you have computation that depends on earlier steps. And that's something that we couldn't do before with just Functor and applicative. So we now have a vocabulary for working with effects. This is what we've been building towards. To sort of summarize, we have functors, which let us work with a single effect. We have applicatives, which let us work with multiple independent effects. And we have monads, which work with multiple dependent effects. And sort of as a slightly more real-world-ish example, you can imagine that this is some composition of values that takes a username and a password, authenticates it, and then draws out what the profile of that user is. And so here, at no point are we sort of explicitly propagating state through or side effects through or error handling or possibly missing values. That all just happens behind the scenes. A flat map, zip map, and so on and so forth. The only gripe about this is that it's kind of ugly, right? Here I'm doing 3 flat maps, and it's already beginning to fall off the right side of the screen. So what Scala provides is syntactic sugar for this. So without getting too much into it, this for comprehension desugars into what you saw in the earlier slide. And this reads really nicely now, right? This sort of reads more or less like an imperative program. The difference now being all the boring stuff, for one, is being handled for you. So if say, getting the username fails, then that whole thing just fails, and that's handled for you. You don't have to explicitly catch or anything like that. If authenticate fails, then that's sort of threaded through. So you sort of are able to now focus on the actual business logic of the code without having to do things like if this double equals null, or if this needs to catch an exception, or I need to mutate this variable, so on and so forth. So that's all I'm going to attempt to cover today. I think I went a little bit fast, but feel free to, I'll be around today and tomorrow, so feel free to ambush me in the hallways and I will give you a better in-depth tutorial if you wish. But what I didn't have time to cover today that's still important, laws. So I mentioned in order for things to be like a functor or applicative monad, you sort of have to implement this interface. Just implementing the interface and type checking it isn't sufficient. We expect these to have certain behaviors. So for instance, one thing is for functors, if I do map with the identity function, that should be the same as doing nothing at all. That's an example of a law. So each of these things have laws that we want implementers to satisfy. We didn't cover computation with more than one effect. So I've been covering option, either state, and isolation. But it's reasonable to say I want a stateful value that can fail. And it's possible to do that. And if you want the Google term, it's going to be monad transformers. But it's possible to do that, and you get sort of the same benefits that we have. And another thing that I didn't cover is tracking IO as an effect. If you were at John's talk earlier today, he did show you what that kind of looks like. But tracking IO as an effect can almost be, it is a talk by itself. So I encourage you guys to go out and see what the literature is like that. This is just the tip of the iceberg. I try to cover 3 very fundamental topics in a short amount of time. So I had to skip over a bunch of stuff and leave out a bunch of very related things. So I encourage everyone here who hopefully feels inspired to go to Rob Norris's talk tomorrow at 11:40, Functional Programming with Effects. We coordinated a bit this year on our talk, so I was supposed to lay the groundwork. Hopefully I did a non-terrible job of doing that. And so you guys can go into his talk with this background, and he'll sort of tell you what the next steps are. If you want to learn even more sort of on your own outside this conference, I encourage you to buy this book called Functional Programming in Scala by Runar Bjarnason and Paul Chusano. It's often fondly referred to as a red book. Buy it, do the exercises, internalize it. It's a really good book, not just for functional programming in Scala, but just functional programming in general. Some stuff I didn't have time to cover that's tangentially related is I mentioned all the effects I've been talking about sort of track very general things like the general notion of state or the general notion of failure. If you want to track even more specific things like I want to track wherever I make a database access or I want to track wherever I make a network call, there's techniques to do that. So like some Google terms, finally tagless, free monads. And sort of a thing that I've been getting into that I want to begin pushing people is think about functional programming in code, but also think about how you can apply it outside of code as well. How can you apply it to larger scale systems? So some examples of this will be Nix or NixOS. So Nix is a package manager that works across operating systems that applies functional programming principles to package management. And they have an operating system built around it. And this is not like a toy project that some person is implementing out of their basement. People at Target, we're using Nix. There are a lot of companies that are using Nix, and people run NixOS as their main distribution. So it's definitely a very real project. And it's interesting if only for the applications of functional programming to something that's not traditionally functional programming related. There's been some hype around reproducible builds, immutable infrastructure, reproducible environments. These are all sort of applications of functional programming ideas to larger scale systems. And one more talk that I encourage people to go see is a talk on Nelson, which will be on Saturday at 9:50 a.m. By Tim Parrott. And that's essentially an application of functional programming ideas to automated service deployment. So applying ideas from immutable data structures to how you automatically deploy systems. And that's all I had for you guys today.
Appreciate it.
Thank you.